Okay, good morning, everybody. I'm here to show let's say, what is going on in CMS for online tracking. So basically tracking a trigger.
I think it's still on the, you need to click once on the, yeah, now it works, now it should work.
Okay, sure. Okay. I can use it. I mean, I can
It might
use
be
it.
off, actually.
Right.
Yeah.
Okay, this is just this is just a summary slide for what how CMS trigger on events. I will not go into details for this, but basically, you know that we have two stages. One is the L1 trigger that we have seen yesterday, and then the one on which I'm focusing on in this presentation is a high-level trigger. This is the one that's basically reconstructing events on a CPU farm as far, for run 2 now in level, also GPUs. And the online tracking is basically, it starts with the pixels and then goes out all to the full tracker. And the core step is happening in the pixel detector. And when we stood in run 2, basically during run 2, we had a traditional CPU farm, so with 1,000 machines, 30,000 physical CPU cores. In this pie chart, you see basically all the contribution from the different subdetectors to the timing that is about 300 milliseconds for CMS. And you see that tracking that includes pixel tracking and let's say the track building. So the auto tracker tracking is about 25% of the time. So it's kind of a big chunk. And it was let's say a trademark for CMS, the idea to have this also for Atlas, to have this iterative approach, in the sense that you start reconstructing tracks that are easy to reconstruct, and then you go, you take away those hits and go after iteration after iteration to reconstruct the one that are more difficult to reconstruct. So this is where we stood in CTD in 2019 in Valencia. And the conclusion was that at the time there was this demonstrator that was built by the group called Patatrack that was trying to port pixel reconstruction on GPU. And at the time it was just a demo that was not intended to go into run 3, at least at the time. But there is an animation that, okay. And the idea at the time was to try to parallelize as much as possible the reconstruction of pixel tracks. How to do this? And the idea was to expose different level of parallelism. As you can see here, this is just a big summary of what is a pixel reconstruction. It goes from the reconstruction of the cluster to the building of the seeds that are the collection of bits, then to the track fitting and also the vertices, so finding the point of interaction. And as you see here, I will not go through all of these different levels of parallelisms are reachable, in the sense that, for example, for the clustering, we can exploit the fact that CMS is built in modules, and so we can parallelize on that. And then on top of that, each cluster can be attached to a single worker, basically, and so we can parallelize on 2 levels. Or for the track fitting, at the end, what we do is just parallelizing on the tracks. So different levels means different kind of parallelization. And this is what is going to be in production now. This is what is running now, actually, CMS with the first collisions that we are getting now. And the final integration happened last year, basically, after 5 years of efforts. And even if targeted run 4, at the end, the things evolved quite rapidly, and run 3 seemed the best chance to have this tested in production, because we had no external pressure from LHC, in the sense that conditions were basically the same as run 2. We could gain experience and also take advantage of the increased computer capabilities to improve our physics. For example, CMS has improved its scouting searches thanks to the fact that we reconstruct the pixel tracks at a much higher rate than we did before. And this is the timing performance that we got. You see that depending on how you couple a GPU with certain CPUs, you get different results. This was run 2, no GPU, and you see that if we attach a Tesla T4 to our CPU, run 2 CPU the gain is big, but is in some kind limited by the fact that there is still this low CPU attached to 24. And then you see that how if we instead use the latest AMD Milan and we attach one T4, this is almost fully exploited, so it's balanced. But in the end, going to the run 3 candidates, so the run 3 CPU that we will use, the best choice is to attach 2 Tesla T4 to 2 AMD to have the perfect balance. And you see here, in fact, this being just show you that the throughput is kind of limited by the GPU that we have. So also the GPU could be a limiting factor. And going to physics, all the run 3 HLT tracking was rethought in order to comply with the fact that we would reconstruct pixel tracks better than we did in run 2 and also faster than we did in run 2. And so in some way, removing one of the was the, again, the trademark of tracking reconstruction for CMS, so the iterative approach. We went for a single iteration where for us, the pixel tracks are the starting building block, and on top of that, we reconstruct the tracks to the outer track. At the end, we see that the physics performance are retained, basically. Okay, this is these are only pixel tracks, and this is with respect to PT and to ETA. You see that the pixel tracks are better. And but when we go to the full tracking, you see that in general we are performing better, and in the backup you can find whatever you want about the resolutions and fake rates. And as regard the timing, again, we are going something like 25% faster with respect to what we had, and this is regarding only the tracker part, because the project went on, and also some calorimeters parts were also offloaded to GPU. And regarding phase 2, I'm posting here some of the expected upgrades. These are not all of them, but are the most important one. For us, as you saw yesterday, there will be an upgraded L1 trigger. That means that we can also reconstruct tracks in some way at L1, at least in the outer tracker, and the inner tracker that is it's made all of silicon and sorry, not inner tracker, the new tracker in general, that is all silicon tracker, and that has a coverage up to ETA 4. This is it. That is not so different from the one that the CTS developed for TrackML. It's a bit smaller, but the concept is the same. And for the phase 2 TDR that was due last year, at the end we stick to what we know, and we developed an iteration that was in some way reasonable to have for HLT. I'm sorry. Oh, no, these are good. Sorry. And you see, at the end, we went for something very, let's say, classic, in the sense a couple of iterations either by pixel tracks and by pixel triplets, and we developed multiple iterations with the idea of trying to keep as much as possible the performance similar to the one that we had offline. And you see that apart from some drops that are, let's say, expected, reducing the timing by factor 6 with respect to offline, we went down. We keep it almost all the performance as they were, with eventually also further reduction if we concentrate on just on the PV that we want to reconstruct. And this is also for PT. Of some resolutions, I will not bore you with this, but you see that at the end, offline and online or different pile-up scenarios are basically the same. And what about timing? You see that our, let's say, chunk of the pie chart is about the 40% of the reconstruction. And this was some of the time that we were speaking about yesterday. So we have 2.2, 2.3, 2.4 seconds. Let's say this is the range depending on the topologies that we quote for tracking in the TDR. And you see 23% comes from the 3% come from the outer tracker, and 17 from the pixel detector reconstruction. As you have seen yesterday, we can, for the outer tracker, we can profit from some new algorithms, like the formerly known segment linking now is a line segment tracking algorithm. Now, there is this chunk that in the first pie chart, if you go back and look at it, is very thin, that is a vertex reconstruction. We are going from tens of vertices to hundreds of vertices. So this, of course, makes the thing change. And you will see tomorrow a quick, a quick plot presentation on how we could eventually offload also this part to GPU. And for the pixel detector, we already did this in run 3. The idea was why not to do this, basically the same thing in phase 2. And indeed, this is what was done. And in the TDR, so we also added this, we ported all the development that we did for run 3 also for phase 2. This was, let's say, much easier than having it to do from scratch, but had some caveats that had to be, we had to watch to comply with the new geometry and tie-up conditions. And this was tested running on CPU on the TDR, and it targets to be fully offloaded on GPU by the end of the year, because there are some things that still are missing. But you see that using the GPU pixel tracks as it was in run 3 for phase 2, we can, keep the same performance that we had for the normal CPU code, say, and we reach about we reached a reduction on CPU, and consider that let's say 43% of the tracking is made in this way offloadable. Another thing is that we, as you saw yesterday, L1 is giving us some tracking object in some way. We started to look into it, and we noticed that we started to look at L1 tracks, but we noticed that it was not something that we could actually use, because at the end they are a trajectory for us. And so missing the hits, we couldn't actually really make advantage of that, because we should have recalculated the hits that were present on the track. While the good thing is that we have some the L1 some vertices already from L1, so in some way we could already, before reconstructing the pixel detector, select some regions that are of interest for us, instead of having to reconstruct fully also locally the pixel detector. And we exploited it by defining some region. This is kind of dummy, but this is the idea was simply to, let's say, restrict the seeds that we use to the one that actually points to these vertices. That is, let's say, a dummy idea, but comes for free in some way. And with this, we reached something like a 20% reduction in timing. And you see that the performance are basically the same. We tested with some sort of displays of topologies also, and it is due to the fact that at the end, talking with the one people, they provided us with more vertices. So at the beginning it was just the first one, the most energetic one. And then you saw yesterday the segment leaking part, that is basically porting each step to be local in the sense that in the way, so that it is easily parallelizable on GPU. This was the map that we were talking about yesterday, where you find all the possible matching between the modules, just simulating all the possible hélices that you have. And so this 23% that at the end is about 1 second, let's say, and also both of them are the order of a second, could go to something that is the order of milliseconds, as we saw, order of tens of milliseconds that we saw yesterday, and the same for the pixel reconstruction. But just a curiosity, probably you have seen this big chunk here that, it's strange, given also the first pie chart that I show you. Usually tracking is the most the part that consumes most of the timing for reconstruction. But what we did in CMS is actually to build a calorimeter that is a tracker in some way, because it's made of millions of channels that are all silicon, or not all silicon, that are most silicon channels. And so this is why tracking is no more the major use of our time. And you see here, this is just a single electron in PyLab 200 for CMS in phase 2. This is a simulation, and you see, okay, you don't see tracks, but actually these are the logical, and it's kind of crowded in some way. But don't worry too much, because at the end, using a bit of the expertise that was developed to rethink the algorithms for the pixel in run 3, So using, for example, the cellular automaton or this kind of algorithm, algorithms for also for the AGCAL, a complete modular, flexible, and also iterative framework has been developed with the CMS that is called TCOL. I will not go too much in detail because this is still a color limiter in some way. But at the end, the idea was to make all of these steps easily portable, already easily portable to GPU. So this has been thought using the experience that we had in Run 3 to be already some way that one step beyond. So the question that I got some time ago was why to invest so much effort? At the end, it's something like an order of 10 people working on this. And one could say, why don't we buy a lot of CPUs? Or why don't we build a much bigger farm that at the end could be doable? So I will let you understand who is the funding agency and who is CMS in this picture. This is CMS. And the point is that let's run some numbers. And we actually did this in the TDR. So we put this black and white. This is an extrapolation from CERN, so from somebody that is actually outside CMS. So it should be, let's say, impartial. You see that basically this is the price for a spec of a CPU. Okay, this is the trend up to now. There is some events, historical events in some way that push the line upward or downward. But these are the extrapolation for the next year. So the point is that in between the pessimistic and the realistic improvement for the price of our CPUs or our cores, you see that we stay between 20% and 15%. If we assume the same trend for, this is some big assumption, but will be in some way reasonable for the GPU price with respect to performance, we observed from in the 4 years a trend that is something like 30% per year. And so making some rough computation at the end in the TDR, we came out with these numbers. That is, if we keep perform that is CPU only for 2028, so for basically, we will have to pay about 1.55 francs, because we pay in francs, per spec. While if we port 50% of the code to GPU, this price is basically halved. And if we go to the 80%, this goes to 0.22, 0.20 Swiss francs. This is counting in all the better, not only the better performance, but also the fact it is taking into account factors like having to rebuild some pieces of the farm or even the energy consumption of these objects. Basically. And yes, and of course, in these years, we learned some lessons that I will leave you just for you if you want to learn something that we already learned. The first thing is that if you want to write something on GPU, you have to go to 4 SOAs. So you have to, in some way, go at least for the moment, to go back to Bayer C in some way, because this takes advantage of the memory collection and is easily accessible to the when you actually write a kernel to run on GPU. So the idea is simply going from something like this, so a struct that is complex, to something that is like this, that has inside already the size of what you want to put in. And this is also something that is in some way a problem, if you want, because you have to stick to fixed size structure. So you have to know before it how much you want to allocate. And this means, of course, that you have to allocate way enough. Few sigmas away with respect to what you expect. Okay. The second part is that you have always to rely on some CPU fallback, because you don't know what will happen in your farm. Maybe some GPU will be, let's say, not available or whatever. So you have always to stick to something that can run both on CPU or on GPU. I'm showing here for example, a block for the the agical reconstruction, just to give you, to show you that it is already basically running on both backends. And so from the side of the configuration, you have different modules that should run on CPUs or on GPUs. This is let's say the framework that has been designed in CMS. There is always GPU to CPU data conversion in order to make the validation also doable easily. And this is user transparent in the sense that you run some jobs just adding a configuration, a modification to the job or not. From development wise, what has been up to now, that the modules that we call that produce objects, basically call dedicated wrappers, either if they have to run on GPUs or on CPU. Then the GPU and CPU share basically the kernel definitions, in the sense that you have these building blocks that runs on one or the other. It doesn't matter. The only thing that changes that on GPU you launch it with by declaring how many kernels you want, and on CPU you simply launch it. But of course, this is not easily maintainable. It means a lot of code duplication, and so the next step is that basically the next thing that will happen in CMS in the next month is the regards portability. And there are many reasons to do this. So the idea is to have a code that runs on multiple accelerators. The first thing is that rewriting the same code for each architecture is not feasible, because it means double, triple, or whatever the effort, depending on what architecture you want to run on. It is easier to maintain because you have a single repository where, and you should have something that goes to multiple backends. This avoids vendor lock-in, because at the moment in CMS, we are only relying on NVIDIA GPUs. So in some way, if NVIDIA decides that, I don't know, they want us to pay double for their GPUs, this is something that we can do nothing with it for the moment. And of course, also, this is something that goes next step, and goes a bit beyond the online tracking. CMS is trying also to include all of this stuff in offline reconstruction. So it's something that we need to go to distributed data centers, not only our data centers, but also HPCs that are basically equipped with any possible accelerator. So we don't know what is there. And in CMS, the search, has been done. Then in the end, the two portability layers on which we realize are Cocos, that we tested were Cocos and Alpaca. So the idea for run 3 was to migrate all of the code to GPU, and for run 4, also trying to think also to other accelerators eventually. And okay, you see here the table. I mean, also SQL was checked. I wasn't involved in this, but it seemed that it was not mature enough for our needs. And this is just an example of how, at the end, the performance are affected by these layers. The Patatrack reconstruction was ported in a standalone container, let's say, in the sense that it doesn't need CMSW, so the software from CMS to be run. And this was useful to prototype different data structure, to, let's say, to play a bit also with the different performability solutions. And the Drupal results are quite, are encouraging, at least for Alpaca, while Cocos was stuck down here. And you see here, this is on GPU. We are losing still some 5%, and we are investigating on that to understand exactly what's happening. And but for yes, this was here. And for this blue line is Alpaca on CPU, and this black line is is native on CPU, so it's performing even better. And I think that's it. I leave you here just some further readings and some of the contribution that I took to write this presentation.
Adriano, is the room still muted, or did we?
Yes, unless you move it.
Get out here.
Go to the green thing
on
the bottom.
There you go. Yeah. Ah, it's not muted. Always good.
Oh yeah, he's been talking.
Oh, yeah, absolutely. Here we go. Well, we go probably for questions. That's good enough. Otherwise, you can go to full screen. Questions, Marcos?
Yeah, thanks very much for this interesting summary of the work. If you can go back to slide 30, because you made some quite bold statements there on the cost savings, and I was wondering how much this is based on evidence, because I mean it's you assume 50% of the full recall to be ported, but you don't have anything which shows how effective it's going to be on a GPU. No? And you assume certain HEP specs equivalent per GPU dollar you are spending, or Swiss franc you are spending, which.
But we, I mean, this were made extrapolating what we have now around 3.
Yeah, but we ported some code which was parallelizable, and you have in your reconstruction presumably certain parts which are much harder to parallelize.
No, sure. I mean, this is so. I mean, this is not taking into account the effort that will be needed to do this, in the sense that.
Yeah, but it assumes a certain efficiency factor for the current. And a certain efficiency factor for the current. You assume certain scaling, what is the scaling you're assuming for the Swiss franc in terms of the equivalent HEP specs is actually going to cover in order to arrive at that cost saving?
Yeah, I understand. I mean, this is, I mean, porting. I don't understand.
So if I think the question is, what is the dollar per F spec 06 for CPU and GPU? Sorry, Swiss franc for
yeah.
How did you calculate?
Okay. No, I mean, we based that.
Actually, how did you calculate HEP spec 06 equivalent on the GPU?
Yeah.
Because that to me is a number which is not. I mean, how do you justify that?
Okay, we assumed basically what we would need as a number of let's say of cards that we would need in assuming that we port 80% of the code with the basics that is our HLT reconstruction that we put in the TDR.
And I think the missing part, what you assume is also that the ported code in future would be of similar ported performance than Buttertrack has shown.
Yes.
Like you show Buttertrack, you say
yes,
speed of 30,
exactly.
and that's what we use.
But consider that this, I mean, if you take this, if you take these, or at least these that has been already tested, and this part that has been developed to be run, and we already have some numbers. This is more than 80% of the pie in some way, or is at least 70% of the pie. So it's already there, this number in some way. We can already measure how many cars we will need in 2028 or in 2021, 31. So we can, let's say,
if one reads the TDR, I mean, but the impression you get is you have this enormous aspect number which you need because you're doing full scan on 750 kilohertz, basically. Yes. Can you comment on what the physics use case is of doing full scan in the trigger for 750 kilohertz? What do you gain?
Okay.
I mean, it's because most of the triggers, let's say more than half of it is leptons, why do you need to reconstruct the full event?
The idea was that we should have left the things untouched with respect. I mean, the goal of the TDR was to leave most of the threshold for reconstruction untouched with respect to what we had in run through. This was the basics.
I'm going against you. It's not your fault. I understand that. I mean, it's the collaboration which is doing that. But it's really striking, right? I mean, because the total amount of HEP specs which you want to install at 0.5 equals the run 4 WLCG share you are having. This is enormous.
Yes, no, for sure that is true.
Well, that's probably a discussion we can follow up on. I don't know if you are if you're also equipped to answer all of this. So I don't know.
Guilty for that.
I mean, because this is the proposed solution that we.
Certain aspects. That's that's almost the if you take your extrapolation figure for what you need for the WSCG, that's equivalent to the WSCG.
No, I understand that completely. Yeah. I mean, that's why we propose to. I mean, because of course in that price of in spec, you are considering the fact that I mean, you can fix the number of GPUs that you want to use.
But that's why I'm saying the whole model depends on this 0.22 Swiss francs per half spec becoming true. Otherwise, what do you do?
Otherwise, I mean, yes.
All right. Well, I think this certainly will not be decided
I mean, it's not my mind.
in this forum. Yeah. However, yeah, room for discussion. Are there other questions?
There's a question there, and
There's a question. Oh, we didn't hear.
No, it was for the last talk though.
Oh, was it for this talk? Okay, I have a question for this talk and for the last talk. And I'm sorry I missed Georgiana's talk. So why are we doing, for example, things like SOA libraries independently, Atlas and CMS? I mean, that does not make any sense to me. And this is.
Yes, I think that would be a good, I mean, a good ground. I mean, there is some work ongoing in CMS to have a good abstraction.
Yeah, and I understand there is some work in Atlas to do the same.
You want to ask it differently? Why is the event data model that's supposed to be developed for common HEP in the EDM for HEP project? Why is it not leading an effort that does this underneath? That's the right question.
Yeah.
For example.
Yeah.
I mean, this applies also to the tracking in general.
I mean, we're doing the portability studies together at least, but I think that the basic libraries should also be done together, or at least studied together, and then we decide. Oh no, we don't like the Atlas solution, right?
But this is happening in the technical forum. The discussions are there, yeah, and partly in the HSF, partly in the
for sure. I mean, the efforts could be shared in more reasonable way. Also, all these efforts in some way, we share a common ground that is kind of big, especially Atlas and CMS. It's strange that we build frameworks from. Not from zero,
right? I mean, why
yes,
not?
yes.
And Alice, I mean, why not? Why don't we make a boost library or a boost candidate library? So, and more, even better people will contribute to it. Anyways, sorry for the.
No, it's the right question. I think from our community, I think we're actually even on the forefront of sharing and now interacting and putting the code pieces together. Good. Then let's thank Adriano again.